The Department of Chemistry at Imperial College is the direct descendant of the Royal College of Chemistry, founded in 1845. 19th century Britain had a proud record in chemistry. For example, more elements were discovered by British chemists than by those of any other country. However, although great men like Sir Humphrey Davy, the first professor at the Royal Institution, and his successor Michael Faraday did much to popularise the subject, there was no institution in this country solely devoted to the teaching of theoretical and practical chemistry. In this we were behind Germany, where chemists such as Liebig and Bunsen had both set up influential research schools. Prince Albert, later to become the Prince Consort, was very active in establishing this country as a centre of culture and of science. In 1844 he invited Augustus von Hofmann, an assistant of Liebig and later to become one of the most eminent of organic chemists, to be the first professor of the Royal College of Chemistry. The college, which later merged with and became a department of the Royal School of Mines, moved in 1872 to the original Huxley building on the east side of Exhibition Road. That building is now a part of the Victoria and Albert Museum. In 1906 it moved to the present site to the west of Exhibition Road, where further building developments have since taken place.
The three-year undergraduate course in this department has always been strongly oriented to practical chemistry. It culminates in a 6-month research project, and it is the purpose of this program to show you the work of 2 students who chose inorganic chemistry as the subject of their research exercise. The first is Andrew Ball, who has chosen to convert a high vacuum apparatus in order to make it suitable for hot atom chemistry to make organometallic sandwich compounds. This technique is currently becoming widely used, and if Andrew's apparatus works well, we hope to use it in the teaching laboratories for the benefit of future generations of students. The class of compounds which Andrew is interested in is exemplified here. In general, the molecules have remarkable thermal stabilities and fascinating structures, in which the aromatic ring binds broadside on to a metal atom. The best known of them is probably ferrocene. The Nobel Prize for Chemistry was awarded to our head of department, Professor Sir Geoffrey Wilkinson, for his work in elucidating this structure and for synthesizing related molecules. Our students make ferrocene and then acetylate the cyclopentadiene ring as part of their second-year practical work. This is part of the original sample actually made by Professor Wilkinson. Andrew is actually planning to make a different compound, dibenzene chromium. It is usually made in 2 stages. The first is a direct interaction of benzene with chromium trichloride in the presence of aluminium as a reducing agent and aluminium chloride as a Friedel-Crafts type activator. The second is an alkaline dithionite reduction. Andrew's method is much more appealing. He will simply bombard benzene molecules with highly reactive chromium atoms. The reaction will be carried out in a vessel which is immersed in liquid nitrogen and at the same time pumped to a pressure lower than 10 to the minus 4 millibar. Benzene vapor, slowly admitted through the central pipe, moves by direct line of flight at this pressure to the wall of the vessel where it condenses. Chromium metal is heated electrically by a tungsten wire until it vaporizes, when it too will transfer, without collision, to the wall of the reactor vessel. The chromium atoms are quite mobile in the solid benzene, even at 77 degrees Kelvin, and quickly react to form the required product, which remains frozen. When sufficient product has formed, the vessel will be warmed up, the condensate will melt, and will be removed from the bottom of the vessel by anaerobic methods. Andrew hopes to verify that he has the right product using proton magnetic resonance. For good measure, he will then oxidize a sample of his compound to the dibenzene chromium cation, which is paramagnetic with 1 unpaired electron, and which will give an electron spin resonance spectrum. These spectroscopic techniques should establish the presence of 12 only equivalent hydrogen atoms. The second student is Vivian Davies. Her project is to unravel the processes involved in the industrial separation of the 6 rare platinum metals. These form part of Group 8 of the periodic table and are all very important industrially. Platinum and rhodium are used as essential catalysts to get petrol from crude oil and to make synthetic fertilizers. Palladium and ruthenium are used in electrical contacts and for printed circuits. Osmium is used in medicine for the study of cell tissue, while iridium, the most corrosion-resistant of all metals, is used in concord and in the sparking plugs of aero engines. Here is a simplified flow sheet for the industrial separation of those metals, which occur mixed together as their ores in nature. With the use of up-to-date techniques, we hope to identify the compounds present in the various dissolved forms of the metals. This has never been done before, and knowledge of the chemical processes involved could help to improve the efficiency of the industrial separations. Before Andrew can perform his reaction, he will need a certain amount of help from the technical staff. Here you see him in discussion with one of our skilled glassblowers. Andrew will need to think out his plans in full detail, draw diagrams and explain his needs to the glassblower. Likewise, he must liaise with the men in the mechanical engineering workshop for a frame to carry the glassware and for various demountable parts which are to be fitted with O-ring vacuum seals. Vivian's first problem is to get her metals into solution. She now takes each of the 6 platinum metals, in powder form since the crude industrial concentrates are also powdered, and tries to dissolve them in aqua regia, a highly corrosive mixture of nitric and hydrochloric acids. Palladium dissolves easily, and platinum too, though more slowly, to give red solutions. The other 4 do not dissolve. Rhodium is attacked by heating it to 700 degrees centigrade in molten potassium bisulfate in a silica crucible. The cooled red melt, on extraction with water, yields a yellow-green solid. The ruthenium is attacked by fusion with a molten sodium hydroxide, sodium peroxide flux at 400 degrees centigrade. The melt is cooled, and on extraction with water gives a deep red solution. The same procedure is used for osmium. The 2 red solutions thus obtained may then be differentiated by adding alcohol. Each is reduced, ruthenium to its black dioxide, and osmium, more slowly, to the purple sodium osmate. Meanwhile, the men in the workshops have received their instructions from Andrew and are using their skills to produce the component parts. Len here is throwing a flange on his glass-working lathe. When made, this flange must be carefully annealed in an oven and then ground perfectly flat. It will form one of the surfaces between which will be compressed a rubber seal in order to make a good vacuum-tight joint. Mick has just finished his job of welding up the frame and tries it out for size on the original evaporator, which is to be converted. Andrew is trying to keep one step ahead of these 2 men by planning the next stage in detail. His exercise is one of logistics and of work organization, as well as of chemistry. Vivian takes her solution of platinum in aqua regia to Sue, the NMR operator. The sample is placed in a very strong magnetic field, which in this modern instrument is provided by a superconducting coil immersed in liquid helium. A weak radio frequency magnetic field is also applied, and the resonance absorption of the platinum-195 nuclei accumulated by Fourier transform techniques to get the best signal-to-noise ratio. The absorption line is written out on the chart recorder, and its position tells us that it arises from the hexachloroplatinate-4 anion. The spectrum of the authentic compound, run earlier, confirms this. The glassware is made. Andrew has too few arms for this job, and is here receiving a little help from Simon, our laboratory technician, who is taking a very keen interest in this project. He needs to know the apparatus well if it is to be used by next year's third-year students, in order to ensure that their experiments go smoothly. Vivian now wishes to take the infrared spectrum of the yellow-green solid obtained from her rhodium fusion, so she first grinds it in an agate mortar. She then makes a paste of the powder in liquid paraffin and places this between two cesium iodide plates. The infrared spectrum is traced out. From this, together with chemical analysis and electronic spectra, she knows that she has identified a rhodium sulfato complex. Andrew's next task is to test his completed apparatus for leaks, to measure the rate of sublimation of chromium and the rate of deposition of benzene. The striations on this glow discharge indicate that the rotary pump is pulling a good vacuum, and the penning gauge at the inlet of the diffusion pump shows a high vacuum there. Andrew is most of all interested in the pressure inside his reactor vessel, so he has fitted a Pirani gauge at that point. All seems well there too, so it won't be long before he attempts his first hot atom reaction. Meanwhile, each of the solutions of Vivian's platinum metals is examined by laser Raman spectroscopy. The solution is placed in a glass cell and spun at high speed to minimize decomposition from the intense laser beam focused on it. By analysis of the light scattered at right angles to the beam, she can elucidate the chemical nature of the dissolved species. Vivian has now completed the flowchart, having established the chemical formulae of the compounds formed in the industrial separations. This completes the major part of her project. Andrew has made all his preliminary tests and measurements. He has weighed out 200 milligrams of chromium metal into the tungsten spiral in his reactor vessel, and now starts his experiment by first getting a good vacuum with liquid nitrogen cold traps in place. The Pirani gauge indicates that the pressure is low enough. The benzene reservoir is full, so Andrew allows the benzene to start coming in. He now turns on the electricity supply to the tungsten wire, which heats the chromium to 1500 degrees centigrade. This will soon be vaporizing at the correct rate to match the rate of deposition of benzene. After about 2 hours, the reaction has finished. The required amount of benzene has been used up, and it is time to warm up the reactor vessel and extract the product, which is in solution in excess benzene at the bottom of the vessel. To do this, a steel needle is passed through a rubber septum and the liquid transferred under pressure of nitrogen gas. The proton NMR spectrum from this molecule will be very difficult to obtain and a stringent test of Andrew's anaerobic transfer technique. It should be a single sharp line because the protons on the two benzene rings must be all equivalent. the slightest ingress of air will cause a minute amount of oxidation to the monocation, and such paramagnetic impurities will broaden the NMR line, possibly to the point of making it unobservable. All seems well with this sample, however, so on to the next stage. Andrew would dearly like to know that there really are 12 equivalent protons in his molecule, so here he is deliberately oxidizing it to the dibenzene chromium positive ion, and will then run an electron spin resonance spectrum. This technique gives a signal from the single unpaired electron which is possessed by the molecule in its oxidized form, but an interaction with hydrogen nuclei should permit us to count how many hydrogen atoms there are. The spectrum is now complete, and we may count here 13 lines with a binomial distribution in their intensities. This is characteristic of 12 equivalent protons, so it looks as though Andrew has been successful. The end products of the research exercise are, first, a written report, and second, a poster which describes the work. Here you see that all the students have prepared their posters, and the poster session is in full swing. Members of staff have carefully read the reports in order to assess the work, but they now take advantage of the poster session to question the students for further evidence of initiative and thorough understanding. As you see, this is kept reasonably informal. It is usually followed by a farewell party, since this is the last time we all meet as a class. The student who has made the best job of a poster, as distinct from the research exercise, gets a prize. In this program, we have stressed that we are proud of our strong tradition for practical work in this department, and that we lay emphasis on good practical work in the undergraduate course. This is not to say that other aspects of chemistry and general studies are omitted, nor does it mean that students do not develop other talents too. We like to think that the course offered in this department, though full and complete in itself, is simply one important part of a more complete education.